Welcome third graders to the Dallas Independent School District STEM Environmental Education Center. We'd like to give a special welcome to a number of schools this morning. The first school is Arcadia Park from the Dallas Independent School District. Next is Libby Elementary from Carthage ISD. We also have Cesar Chavez from Dallas ISD with us today. We would like to welcome Spicewood Park Elementary from Southwest ISD, Marsalis Elementary from Dallas ISD, and the girls at the Solar Preparatory School for Girls in the Dallas Independent School District. Thank you so much for coming to our virtual field trip this morning. We wish you could be here in person, and we're going to do our best to make you feel like you are here through a virtual field trip experience this morning. If you are watching this and have not registered for this field trip yet, you can still do that by going to www.tiny.cc/EEC register. There you'll fill out a short form to get yourself or your class registered for this field trip. We just use that information for our attendance purposes. And today's virtual field trip is going to be all about force and motion. During this virtual field trip, students will discover that forces cause change. Students will observe how position and motion can be changed by pushing and pulling objects. Students will also observe forces such as magnetism and gravity acting on objects. So we're going to start off this virtual field trip by exploring how forces cause change. That's going to be led by Mrs. Fuller. Next, we're going to learn that energy exists in many forms. That will be led by Miss Nash. Third, we're going to explore how position and motion can be changed. That will be led by Mr. Ramirez. And to wrap things up, we're going to learn about the force of magnetism with Mr. Monroe. While we're doing all of that, you can ask us questions, and we encourage you to ask questions. But since this is a virtual field trip, to ask a question, you'll need to go to www.tiny.cc/EEC-question-answer to type in a question and submit it. Once you do that, we'll be able to read it and we'll answer it for you. You can ask as many questions as you like, and we'll do our best to get through all of them in the time that we have with you this morning. So let me stop sharing my screen here. We're going to start with that investigation on how forces cause change with Mrs. Fuller.
Good morning, students. My name is Mrs. Fuller, and this is Lauren the chicken, and we're going to be talking about how forces cause change. We're going to talk about different kinds of changes and different kinds of forces. But we have three words that are all very connected to each other when we talk about force and change. The first word is energy. Energy is the ability to do work. The second word is force. Force is a push or a pull. It can start something in motion. It can speed it up. It can slow it down. It can stop it. It can change its direction. We've got all different kinds of forces we're going to be examining today. Now, in order to have motion, motion is moving. So moving is caused by forces, and we get the ability to do that work with energy. So remember, forces cause change. So let's talk about some changes. One of the changes we're going to talk about, this Lauren the chicken laid an egg. That's her job. That's her work. She is a hen chicken, and she pushed this egg out of her body. So that was a force, a push. So where did she get the energy? Remember, it's energy, force, and motion. Where did she get the energy to do that? Well, she got the energy from her food. She eats worms. See the worm? I'm going to offer it to her. You want a worm? Yeah, she wanted a worm. Okay, so I'm going to put her down so she can eat the rest of her worms. So we'll talk about some other changes, oopsie, caused by force. Okay, so one of those changes is breaking. You can break things. So let me put some gloves and some safety glasses on. Here at the Environmental Center, if you've ever been out here, you may have seen our fossil pavilion. Our fossil pavilion is full of a special kind of sedimentary rock called Eagle Ford Shale. It's a very important formation here in the state of Texas. Some of it is fossiliferous. The Eagle Ford Shale we get is full of shark teeth and snails. So the boys and girls put on safety equipment, and they use rock hammers to break the rock. They use the force of their arm with a hammer. The hammer is the tool that does the work. and they break it apart. And I think I've got a shark tooth right here. I can show you. So you see that? Can you see that right there? Yeah, how about that? So we were lucky today, right? All right. So that was a force, and I changed the rock. I broke the rock. The rock's not going to go back together. So that was a permanent change caused by force, the force of the hammer hitting the rock, and it used the muscles of my arm to do that. All right, now another one that we're going to look at right now. It's fall, and I know you've got pecans falling in your schoolyard and at the park close to your house. I bet a lot of you are cracking pecans open to make a pecan pie. So here's a pecan. It's a native pecan. It's real small, and this is a nutcracker. It's a lever, and I'm going to put force on the pecan. Did you hear that? To crack it open and to reveal the pecan inside. Now that's one kind of nutcracker. I've got one that's a little bit more sophisticated that has blades on the side. And this one will take the pecan and just break off the shell, revealing the pecan inside the shell. So that was force from my hand using machines to cause a change. And the change was I cracked open the pecans. Here's another one. I don't know if you use these at your house, but it's just a little piece of plastic or rubber that you put on top of a jar in order to open it. I can't open a jar without this. Some people can, but I can't get to the pickles unless the jar is open. So I'm going to put force, the force of my hand, using this little tool right here to force the lid open on the jar. I got it open. There are the pickles. I'll eat those at lunchtime. And so I caused a change by using the force of my arm and the aid of this little plastic thing to open up the jar of pickles. Now remember, force is a push or a pull, and it can be by direct contact. That's what I just did. I put my hand on the school bus and I pushed it forward and I pulled it back. That was direct contact. Another way is wind or moving air. Now, I don't have wind in my room, but I do have some moving air in my lungs, and I can blow. This is an anemometer. This is a toy one that a real one would measure wind speed. But let's see if I can put a force of moving air on the anemometer to get it to move in a circular motion. And there it goes. Now you notice it didn't spin real far, and that's because another force called friction slowed it down. Friction's job is to slow things down, so that's another force. We also have the force of magnetism. You're going to have a whole segment just on magnetism in just a minute. I'm going to also show you gravity. So let's get our gravity stuff here. We'll make a ramp, an inclined plane, and we'll have a Paws Patrol fire truck. I'm going to put him up here. I'm not going to push or pull him. Gravity is going to pull him. When I let go of his wheels, he's going to go down this ramp by the pull of gravity. That's a force, gravitational force. And there it went. So that was gravity. Gravity is the force that holds us on the planet so we don't drift off into outer space. It's a pretty good force. All right, let's see what else we have here. Oh, let's make some limeade. So I have a lime, and I'm going to put it inside the juicer. Here's my lime. Put it inside the juicer, and I'm going to force this lever, this juicer, and the juice will come out of the lime and go in the jar, well, the glass. And it caused change. It caused the juice to go from the lime into the glass and also made the lime very flat. So that was a change caused by the juicer, using the force of the lever in my arms. Here's another one right here. This is a top. I know you're familiar with those. I'm going to push it with my thumb and my forefinger, and it's going to spin in a circle on the floor. So let's look at another one instead. This is a little caterpillar who has a spring inside. I'm going to wind the spring up, and as it releases its energy, it's going to push the caterpillar forward. It's going to go in one direction. It's going to go forward, straight. All right, so we've got our three words: energy, force, and motion. Energy provides the ability to do work to the force. The force is a push or a pull or friction, and it causes motion. If you have any other questions about force causing change, Mr. Broughton will be happy to answer those. Thank you so much.
Thank you, Mrs. Fuller. The question that came in was from Haley from Solar Prep, and she asked, what are airplanes made out of? Airplanes are made out of aerospace grade aluminum, steel, other metals and alloys and composites. Whatever the materials they use, though, they are going to be stiff, strong, resistant to corrosion, and lightweight. But what's interesting about that question is that airplanes have to do with forces, and some forces that you'll hear if you ever study how planes fly is lift and drag. So do some research on that, and I think you're going to be interested to find out some different things about forces and how they affect airplanes. All right, now we're going to learn about forms of energy with Ms. Nash.
Hello, welcome to my classroom. I'm Ms. Nash, and today we're talking about forms or kinds of energy. So we have lots of different kinds up here on my chart. Let's start with light, because that's kind of the most important one for life on our planet, particularly the light from our sun. So light from our sun, plants figured out that they could use that light energy for their own life, to live. And they used energy from the sun, that light, CO2 from the air and water, and they make their own food, photosynthesis. And they stored that, some of it they used to grow, but then other parts of it they store as chemical energy. And we animals can come along and eat them and get that chemical energy for our own, for ourselves. So somebody came along and ate a big bite out of that leaf. So that, I don't know who that was, it wasn't me. I don't think this one would taste very good, but some other kinds I do like to eat. I bet you do too. So all that yummy food that we eat starts from that light energy from the sun. Another kind of energy that we have all around us that you're using right now, that sound energy. Inside your ear is a tiny drum that receives the vibrating air and turns it into sound we can hear. So sound energy is vibration. I've got my little symbols here, and if you hear that sound, it's vibration. So that they're vibrating, it goes in your ears. I can do it again, and if I touch them, then I stop the vibration, and the sound stops too. A really fun thing to do is to do your own little experiments with sound. And sound varies in volume, how loud or soft, also in pitch, high or low. So just using rubber bands and a box, you can make your own kind of prototype of a guitar. And if you stretch them tight, 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 you get a high sound. Less tight, less tight. So you can vary the pitch just by how tightly you pull that rubber band. So it's a really fun thing to do and experiment with. Another form of energy is heat energy. So the sun gives us light and heat, but heat is also produced in other ways. So we, if we metabolize that chemical energy we got from plants, we produce heat because we're mammals. And in the winter, we're going to put our jackets on or turtleneck on to keep warm, keep our own body heat in. So I can rub my hands together and make them hotter with friction. Back and forth, it's creating more heat energy. I've got a little toy here. with a liquid inside. And like my hand's hot enough, then watch what happens. That liquid goes up inside. Looks like it's boiling, but it's not. My hand's not as hot as it would be to boil water. It's a liquid with a lower boiling point inside. So as my hot hand, the heat from my hand is making it take up more space and pushing things around, up and down through the little, called the hand boiler. Kind of a fun tool to explore heat energy. Then we have our chemical energy, like we have in our food. We've got electrical energy that runs our light bulbs here. Also, we store that in batteries to turn on flashlights and other things. Okay. We use that electrical energy to charge up our computers, our phones, all that good stuff. We also got, oh, I forgot about your car runs on stored energy. So just a little, not gasoline. I don't want to bring that in the classroom. That's super dangerous. Just a little can of fuel that we take backpacking. And you can hear it's got a little bit left in, not much. It's a liquid. It's under pressure in this super strong little can. But when I open up the valve, it's in here. See that gas coming out? And I can light that gas. I can put my little pot on top and I can cook my breakfast and my dinner. So the gasoline that you use in your car is also liquid. It can be changed to gas inside the motor to burn and then run your car. Now, mechanical energy is another kind of energy that's really fun to explore and do little experiments. Now, Ms. Fuller showed you a lot of little toys and little mechanical energy moving things around. So mechanical energy can be potential, meaning waiting to happen, or kinetic, meaning actually moving. So you can make yourself a ramp like Mr. Fuller showed you, and we can do a little test. Okay, you run a little test. So I've got two little balls here, more or less the same size. This one's styrofoam. It's got a lot of air in it. It weighs hardly anything. A little rubber ball, heavy, okay, more mass. So if I start them, we're gonna have a race here. I'm gonna start them both at the same height, okay, above the table. And which one would you predict is gonna win the race? Let's see. 1, 2, 3, and oh, my little rubber ball won the race pretty easily. Okay. So because it had more mass than this one. So gravity was pulling it a little harder. Now if I take two styrofoam balls, one's got spots on it, and I raise up one of my ramps. I got the same. Remember when you run an experiment or a test, you always want to change one thing only. So here on the first time, we had two different kinds of balls. The second time, we're going to put the ramps at a different height. So we're changing one thing at a time. So now, which one do you predict is going to win this race? Okay, we're going to put the spotting one up higher. And 1, 2, 3. And wow, the spotty one won easily. Okay, because gravity was exerting more of a force on it because it started up higher. It had more potential energy that translated into more kinetic energy. And so it won the race. Another example of that is this little toy called Newton's Cradle. They're really fun to play with. They have these heavy little metal balls there. And if I pull this one back a little bit, okay, it's got potential energy now. I'll let it go. And that same energy is transmitted all the way through. Now, if I raise it up higher, it's going to have more potential energy, right? What do you think is going to happen now? So again, we get the same kind of energy transmitted. If I take two of them, now I've got more mass, right? Okay. Now I've got more mass and more gravitational potential. And wow, so really kind of a fun toy. It's a pendulum swinging back and forth. Okay, now, one thing I'd like you to try to do is to think about all the different kinds of energy around your house and also outside. So it'd be good to go compare the kinds of energy you find inside your house with the kinds you can find outside. So if I have a poster here, I wish we could be outside by the pond, see if we could find our beautiful friend there, the great blue heron. They're beautiful birds. We have them out here. You might see them at the lakes and the parks if they've got water. So here we've got a lake. The sun is shining. I think it's going down here, but it was giving us light and heat all day long. The sailboats are using wind energy. The birdies are using their own their own energy to fly. Okay? And there's a man out here, a woman who knows, in a boat. They might have a flashlight. Okay? The sun is helping these plants grow. The little bugs are eating the plant, the fish are eating the plant, the bugs, and the great blue heron is waiting. Potential energy to reach out, kinetic energy, and grab a fish to eat it, and turn that chemical energy into great blue heron. So you make a chart, doesn't have to have all of them on here. I left out nuclear energy because I don't have a nuclear power plant in my room. Safety tip. You might just do light, sound, and heat or electrical energy. And so inside we have the light bulbs. Okay. Outside we have the sun. Sound inside, we might have a television on. Outside we might hear the birdies. So you can make a little chart and compare the kinds of energy you find inside with the kinds of energy you can find outside. So have some fun, make some ramps of your own, make some guitars of your own, and look around for energy. Thank you. And if you have any questions, Mr. Broughton will be glad to answer.
Thank you, Ms. Nash. Two questions came in. One is from Elizabeth. Do you have animals? Yes, we do. In fact, you're about to see some more animals with Mr. Mears in a minute here. And Hannah asked, where do you work? We are in Seagoville, Texas, which is 20 miles southeast of Dallas. We usually do field trips related to earth science and life science, but we are excited today to do one on force and motion because force and motion affects the earth and all living things on earth. So even though we normally focus on other things, it's fun to do something a little different today with y'all. But I'm going to turn it over to Mr. Mears now because she is going to explain how force and motion can change position and direction of objects, including animals.
Hi, my name is Ms. Ramirez, and in this segment, we're going to be looking at position and motion and how it can be changed by pushing and pulling objects. So in particular, we're going to be looking at the motion of swings, moving balls, and wagons. And the way that we're going to explore position and motion is by exploring an animal friend, Pepper the chicken. So as we learn about Pepper the chicken, be thinking about how does Pepper use swings, balls, and wagons to change position and motion. So since we're going to be learning about Pepper the chicken, I'm going to go ahead and bring her out for you guys. She gets her name Blue Silky Chicken because these are a special type of chicken that have blue skin around their ears. And you can kind of see a little bit of it there as she turns her head. They also get the name Silky because their feathers are super soft. So I know y'all can't touch her, but I'm touching her right now and she is very soft. Oftentimes kids think that it's fur that she has, but they're actually just super soft down feathers. So this is Pepper the chicken, and we're going to be using her in some of our videos and demonstrations today. So I'm going to go ahead and put Pepper the chicken up, and we're going to look at how Pepper uses rolling balls today. So we're going to see that motion of rolling. So I'm going to show you an example of one of her favorite toys. So Pepper is an indoor chicken for the most part. So I have lots of toys for her to keep her occupied and busy so she doesn't get bored. Sort of like when you guys go to the zoo and you see like different toys inside the animal habitat. That's just to keep the animals occupied and keep their minds stimulated since they're not running in the wild with all those fun things. So here's one of the toys she has. It's a rolling ball. And I actually open it up and I can put treats inside, things like little seeds. And then also her favorite treat to eat are mealworms. She prefers them alive, so that's what you can see here. So I put those treats inside the ball and Pepper has to exert a force. So she actually has to do work to get the treat to come out. And I'm actually going to demonstrate how it works, because sometimes Pepper doesn't like to be on camera and she doesn't like to perform for me. So I'm just going to show you. So what she ends up doing is she actually has to exert a push. So she has to push the ball either with her feet or with her legs, and she has to make the ball roll. So as I push the ball, be thinking about how is the ball changing in position and think about its motion. So I'm going to push the ball and you can see treats fell out. So describe the motion. So I would say it has a rolling motion, and I kind of, if you just push it just slowly, it doesn't move a lot. But if you apply a lot of force when you push it, it goes really far. So we can describe the position change as it went from the right to the left, or it went from the red squiggly line to the purple squiggly line. So that's how we can describe its change in position. We can describe its motion as rolling. Now, what do you think? What force do you think stops it from rolling? So the force that stops things from moving or slows things down is friction. And friction is just a force that's applied when two objects are coming in contact with one another. So my favorite example is, think about if you're on a nice smooth floor and you have your socks on and you like to slide across the floor. It's friction that's eventually going to make you slow down. So friction is an example of a force that slows down motion. So that's how Pepper uses things like rolling balls. Now, the next thing we're going to look at is how Pepper uses swings. A swing is a type of pendulum, and you saw an example of a pendulum with Miss Nash with the Newton's cradle. So a pendulum is just a simple device. It's like a swing that works based on the force of gravity. So remember, gravity is a force that is trying to pull things down. So let's take an example of this little pendulum here. So if I release the pendulum, the force of gravity is what is going to pull it down. And it keeps swinging due to inertia. And of course, it's going to eventually stop because of gravity and also some air resistance as well. You guys are familiar with swings. If you've ever played on a playground, you have your friend behind you. Your friend applies a force, a push, that sets you in motion, and you start to swing back and forth. It's the pull of gravity that is making you pull down, and eventually that air resistance will make you stop altogether. So let's see an example of how Pepper uses swings or pendulums. And I have an example of another one of her favorite toys that she has outside, and it is a chicken swing. And unfortunately, I tried putting her on it earlier, and she just flew right off. So I just put a little cutout of her on the swing for demonstration. But chickens are prey animals, so that means there's lots of animals that would love to eat them. So oftentimes, we'll see our chickens that are running around outside. We'll see them perched on things, or they roost. So sometimes we'll see them perched on top of some of the railings, perched on top of some of our cars, or perched on top of, the lower tree branches and such. So they're just doing that to get off the ground, maybe survey their surroundings, or to escape predators if they see any. So Pepper here has a swing that's outside, and she does go on it. So the way the swing works, if I apply a push, it's going to start that motion, and it's going to swing back and forth just like a pendulum. Eventually, the pull of gravity will start to pull it down, and air resistance will also slow it down as well. So what I'm going to show you guys next is just a couple of little videos of how Pepper is influenced by pushing and pulling. So let me go ahead and share my screen with you guys. And we'll go ahead and show it. The internet's been kind of weird lately, so we'll see if it plays. Let me go ahead and pull up that PowerPoint, and we'll try it in full screen first. If it doesn't work, we'll just do the little screen. So here is pushing and pulling. So here's a video of Pepper being pulled by a wagon. So I am exerting a force. I am pulling her toward me. You can see that wagon moving. You can see her feathers kind of blowing in the wind. And the reason it's so much easier for me to move Pepper in that wagon is because the wheels on that wagon are an example of a simple machine. So the simple machine that's used in a wagon is a wheel and axle. And that is simply what helps me do that work easier. The next thing we have is Pepper in a rolling chair, and I am going to apply a force. I'm going to push her on that chair. So that pushing is what starts the motion. If I do a little push, she just moves a little bit. If I do a big push, she moves a lot. So the amount of force that I apply will affect how far she moves. And she's enjoying that little fun little ride through my classroom. And there she goes. So that's pushing and pulling. The next thing we're going to look at are swings. So again, a type of pendulum. We saw how Pepper used a swing. So now let's see how another animal uses a swing. So as you watch the video of this little chinchilla, describe the changes in position and motion. And then think about what forces are affecting the chinchilla. So you can see the little swing is set in motion and it's rocking back and forth, just like the Newton's cradle that Miss Nash showed you guys. And then here's another video of a little squirrel on a little playground. Something fun that you guys can do to watch animals is make a little playground for wildlife at your school garden or in your school playground. That climbing tower is just made out of soup cans. You can make a simple swing using sticks or a piece of wood and then tie it together with rope. You can make a little walking line just using string and stretch it across two things. So you can make a fun little playground for wildlife, and you can study how those animals are moving and how their position is changing. So I love to just look outside my window and observe all the wildlife that we have out here. Our next thing is a picture of my former chinchilla, Chinchy the chinchilla. For those that have been out and visited us before, you probably met Chinchy the chinchilla. He has been by far my most favorite classroom pet. Unfortunately, he passed away last year, so this is just a little picture in memory of Chinchy the chinchilla. And the last thing we're going to talk about is the motion of balls or spheres. So here we have an example of ball bearings. Now, I never knew what ball bearings were until I started doing this presentation. Just last week, Mr. Monroe was asking me if I had some ball bearings for his experiment. I didn't even know what they were. So I did some research and I found that ball bearings are actually found in a lot of things that we use in our everyday life. So for example, those fidget spinners that you guys like to play with, they have those little metal spheres inside them that help that device spin or move. Ceiling fans also have ball bearings, and that is what helps the fans rotate. Also, your bicycles have ball bearings in them to help those wheels move. So balls are a device or a tool that we can use to help things move or rotate. Now let's take a picture of this, or observe our nice little hamster over here in his hamster ball. Describe his motion and also how he's changing positions. So my thinking question for you guys is, do you think the hamster moves faster inside that little hamster ball, or do you think he moves faster on all fours? So how do you think that hamster ball helps him? And then my last thing, I just have a reflection question for you guys. See if you can give 2 examples of when you have had to push things and 2 examples of when you've had to pull things. Think about, did you use any tools to help you? And then think about, how does gravity or friction affect you and those actions? So now I'm going to stop sharing my screen, and we're going to go ahead and pass it back to Mr. Broughton, and he's going to answer any questions.
Thank you, Mr. Ramirez. One question that came in is from Margaret from Solar Prep. What are atoms made out of? Atoms are made of protons, neutrons, and electrons. And then another question is from the students of 3C at Arcadia Park Elementary. What are some forces that students would experience on the playground? You could experience a pulling force on the playground if you climb up anything like a jungle gym. You would be pulling yourself up off the ground. You would experience gravity if you slide down a slide. It's gravity that pulls you down the slide. And you would experience a push if someone pushes you on the swing. So you can experience lots of different forces on the playground. Now, 2 other questions that I'm going to let Mr. Monroe answer here in a minute are, why are magnets attracted to each other? Maggie asked that from Solar Prep, and he's going to answer that for you when he starts here in just a minute. And then the other question is from Julie, also from Solar Prep. What is the biggest magnet in the world? Okay, Mr. Monroe, I'm going to let you present and answer those questions as you do your presentation.
Okay, good morning, students. My name is Mr. Monroe, and I'm going to try to answer those questions that Mr. Barton has brought forth to me, but we're going to go ahead and get our investigation started about magnetism. We know that magnetism is the ability of, or the property of some material to be able to attract other items that are made up, or their matter has a certain content of iron, steel, or nickel in their content. And they will attract that type of metal. And I think one of the questions was, what's the largest magnet in the world? I'm going to have to look that up and do a little research on that. But I can remember some of the larger magnets that I saw when I was very young was a magnet that was used to separate different metals in a scrap yard or a salvage yard, which had lots of different metals that were going to be in the process of being recycled. Iron, steel, aluminum, copper, all kinds of junk metal that had to be separated was separated by a magnet. Now, when we talk about magnets, probably the most common magnets that you are aware of are the bar magnet, the horseshoe magnet, and maybe even a ring magnet. But I'm here to tell you there are magnets all around us in our everyday lives. And, you know, I was really curious when I was young, and I thought magnets were magic. And later on, I found out basically it is science dealing with the properties of certain matter, okay? Now, wanted to find out who actually discovered or invented the magnet, and I couldn't find out who it was. But there are lots of stories about how magnets were discovered. And one story, it's a little bit long for me to tell you, but it was an experience that a young person had when he was out in nature. It is a form of a natural magnet found in a rock formation that is called magnetite. Another name for it, it is called lodestone. It looks just like this. This is a lodestone. This rock is made out of magnetite. Now, talking about those magnets that are very common to us, you know, the strongest attraction, the strongest pull that a magnet has is found in the ends of those magnets. For example, the bar magnet that I showed you, this end is marked with an S, that stands for the South Pole. This end is marked with an N, that stands for the North Pole. That's where the strongest attraction, the strongest magnetic force is located in this magnet. Same way with the horseshoe magnet. S stands for South Pole, N stands for North Pole. Strongest attraction of this magnet is located there. And of course, the ring magnet, one side, probably the North Pole, the other side, the South Pole, and that's where the strongest pull of that magnet. And they come in different sizes. Even a horseshoe magnet, you probably would be able to find one smaller than this. And of course, I have a couple of bar magnets that are very small. Now, students, listen. Magnets are attracted to different types of material. Most of the material that's going to be affected by the magnetic force that surrounds a magnet is going to be those objects that have iron or steel or nickel in their makeup. I've got a few items in this Petri dish that I'm going to put in another Petri dish, and we're going to find out if we can separate some of those materials, some of these objects, because of what they're made out of. I'm going to put a nail, a brad, which is gold in color. I don't know whether a magnet's going to pull that. I'm going to put a small ball bearing, like you heard Ms. Ramirez refer to, which is just a small steel ball. I'm even going to put a rock. Let's see here, a paper clip. Another type of paper clip. Oh, how about a little money? I'm going to put a penny, okay? Put a penny in. I'm going to put a pop top from a soda can. And let's see, how about a screw? That's probably enough. I don't have much time to work with you guys, so let's do this real quick. All right, I'm going to Scan this magnet over this material and see what's going to be attracted to it. Wow. Well, I did pick up quite a bit of stuff here. Boy, look, it's trying to pick up that ball bearing. There we go. We got the ball bearing, the nail, the paper clip, the screw, and even the brad, which is gold in color. So you know what that tells us? These items that are attracted to this magnet have iron, steel, or a bit of nickel in their makeup. They're made up in their matter. What it did leave, and I'm going to put this down, it left the penny, and we know the penny's made out of copper. It left the pop top from the soda can. It's made out of aluminum. And I guess the rock doesn't have any iron or steel or nickel in it. It left it. And I had a feeling that it was going to leave this paper clip because the paper clip, this paper clip, is made out of plastic. Now, attraction means it's a pulling action. These items were pulled to that magnet. Now, what about a pushing action? Well, that can happen between magnets. And the way that it happens between magnets is, you know, there's a north pole and a south pole to a magnet. Where have you heard that before? No, our planet has a north pole and a south pole, right? So could it be that our planet, the planet Earth, is just a great big magnet? We'll talk about that in just a little bit. But anyhow, if I take the north pole of this small bar magnet and the north pole of this small bar magnet, and I try to get them together, I can't do it. They're pushing away from each other. They're repelling. To repel means to push away from each other. Now, if I change and I take the south pole of this bar magnet and the north pole of this bar magnet, look what happens. They attract to each other. Now, students, listen. Magnets are all around us in our everyday lives. They're used in the medical field. They're used in our homes. They're used in computers. They're used in electrical power plants, which generates electricity to light our houses and other industries. And they're used in robots. And students, listen, they're used in another tool that a lot of people, when they're going to an area, and maybe you've gone with your family to a park or gone camping or gone hiking. I like to spend time in the outdoors myself. And when I'm in an area that I am not familiar with, that I might get lost in, do you know what I carry with me? I carry something called a compass. Looks just like this. A big one, a model would look like this. And on that compass, you will find N for north, S for south, E for east, and W for west. A compass will help you find your direction. Simply because, remember when I talked about the planet Earth? The top part of our planet, we call it the North Pole, right? The bottom part of our planet, we call it the South Pole. Our planet acts like a very large magnet because people refer to the North Pole as being the magnetic north. And inside of a compass, guess what? There's a magnet. That needle is a magnet. And it is always drawn to the north or the magnetic north. Now, I have made a homemade compass here. And it's got a magnet suspended by a string. And I know that north is that direction from my classroom because the compass told me, and I know over the years that I've been here, that's the way it is. Now I'm going to place this and we're going to see if it's going to find the north. I'm going to give it a little tap and let it work its way because we're running out of time. It's working its way around. And it's probably not good. It's going to take it a while to stop, but it's working its way to where it's eventually going to be facing that direction. Students, it's really trying to work, but we really don't have time for it to be still. Now, the only thing that would mess a compass up is if there are other magnets around that are close with their magnetic field being within that area where it would really impact the direction of the magnet in the needle in a compass. And if you were on top of a mountain that had lodestone, your compass would not work. It would probably go haywire like this because there would be an influence of that lodestone or that magnetite. It would go really crazy, okay? Now, I have run out of time, students, and I hope I've been able to help you get a little understanding about magnets, and maybe I've had a chance to answer those questions that those students had. But as far as the largest magnet in the world, whoo, I'm telling you, I'll have to do some research on that, okay? Now, I'm going to turn it back over to Mr. Broughton in case some of you have some questions, and I want you guys to have a good day the rest of the
Thank you, Mr. Monroe. I'm going to share my screen here to do a quick recap of what we did today. So today's field trip was all about force and motion. During this virtual field trip, students discovered that forces cause change. Students observed how position and motion can be changed by pushing and pulling objects. Students also observed forces such as magnetism and gravity acting on objects. So we explored how forces cause change. We learned that energy exists in many forms. We explored the position and motion can be changed, and we investigated with magnets. Thank you so much for joining us this morning. We appreciate you taking the time to learn about force and motion with us. We would like to know what you think about today's field trip, and you could let us know by going to www.tiny.cc/EEC feedback to fill out a short feedback form about today's field trip. We hope to see you again in about 3 weeks, and have a great rest of your day. Goodbye.